Okay, maybe let's start. So welcome everybody for today's session of the seminars for the kinetic program at Isaac Newton Institute. So today we will have two online talks. First one will be by Helene Hivert. He is from École Normale, École Centrale de Lyon. Thanks, Helene. And she will be talking about the asymptotic-preserving scheme for concentration phenomenon Lotka-Volterra parabolic equations. Yeah, thank you. Stage is yours.
Okay, thank you, Ava, for the introduction, and thank you for this very nice invitation. Yes, I will present a very recent work we did in collaboration with Vincent Calvez and Ava Yoldash during her postdoc in our team. And it is not about kinetic equations, but it is about the design of asymptotic-preserving scheme for an equation which is by nature which by nature has multiple scales. And so it is related to some problems that are considered in the numerical analysis of kinetic equations. I'll start with an introduction to present the problem. And in fact, we are looking at a population which is structured in a phenotypic trait and in time. So the quantity under study is denoted n for the moment, and it depends on the time t and on the phenotypic trait x, which belongs to Rd. And the question is to understand the behavior in time of this density of population. And we suppose that it is driven by two phenomena. The natural selection, it is described by this quantity R. It is called the net growth rate, and it describes the births and deaths and deaths in the population. It depends on the phenotypic trait, meaning that some traits are better adapted than the others. So it means that some traits may live longer, for instance, or have more children. Okay, and the quantity I in this net growth rate is a measure of the total population. It's the burden of the total population on the environment. And the second phenomenon that appear is mutations. And in this in this talk and in this work, actually, we consider the toy model in which the mutations are described by a diffusion around the trait of the parent. Okay, and the question is to understand to understand the behavior of the population in a long time and small mutations regime. So we suppose that the trait of the kids is not very different from the traits of the parents, and we consider the evolution of the population when time evolves, and so there are many generations. This study was done in, for instance, in these papers. It's for the particular equation we are looking at, but it's a more general problem if we only consider density of populations. So the equation we are considering is this one. So you have the evolution in time of n. You have the mutations, and it is rescaled with a parameter epsilon, which is it is expected to be small since we are looking at small mutations. And here is the impact, the selection, the net growth rate, R, and I, the total population weight is the integral of n over all the traits, and psi here is a very smooth function which acts as a weight on the trait space. Okay, and we are given an initial condition such that in fact this I is well defined at time 0. When you consider this problem and when you make epsilon go to 0, it is well, with numerical simulation at least, it is easy to remark that when epsilon goes to 0, we have a concentration phenomenon, meaning that in fact n converge to a direct mass located at a particular trait or some particular traits. So it may be a sum of direct masses. And in fact, this means that in long time, the population concentrates around some traits that are supposed to be the best adapted traits for the population. But to study this concentration, it is actually a bit complicated if we consider only this quantity n, because here n is expected to be very regular. In fact, you can consider that this is a reaction diffusion equation, and thanks to the Laplacian, you can expect regularity from n. But when epsilon goes to 0, the Laplacian vanishes, and then you lose the regularity. And in fact, at the end, you have only direct masses, so you can't expect more than a measure of regularity. So it brings problems in the analysis, this loss of regularity. And one way of eluding, in fact, the problem is to change the unknown and to apply a logarithmic, an exponential transform. Well, it's a logarithmic transform of n, and meaning that n is exponential minus quantity u over epsilon. And it is expected, thanks to a maximum principle, that u is positive when epsilon goes to 0, and in fact we can prove it can be proven that u is greater than a constant times epsilon, so it can be negative but not much. And u is coercive, it goes to infinity when x goes to minus or plus infinity, and it means that when epsilon goes to 0, n concentrates at the place where u is equal to 0, and u enjoys much more regularity than n when epsilon goes to 0. So the analysis is much simpler with this quantity u. So if we plug this transform in this equation for n, we obtain another problem for u, which is the time derivative of u plus something which is actually Hamiltonian. It's a nonlinear function of the gradient in x of u, and this nonlinear function is convex. There is still the trace of the Laplacian, then multiplied by epsilon, and this is here is the net growth rate. And nothing changed in I, except that we replaced n by exponential minus u over epsilon. And we are given an initial condition, which is in fact the transform of the first initial condition. And the problem, we can reformulate the initial problem. So to understand the behavior of the population in no time and small mutations regime becomes understanding the asymptotic behavior of u when epsilon goes to 0. Okay, and for this problem, we have there are some results, but some hypotheses are needed. As I said, the function psi, which is in I, has to be smooth and bounded. It's not very important. It's only technical, but you can consider that psi is 1. There is no loss of the generality. There is another hypothesis. This is that there are two constants, I small m and I capital M, such that for I small m, R is always positive, and for I capital M, R is always negative. It is important. It enables to localize actually the I at the end. Another another important assumption, which is related to the previous one, is that R is decreasing with respect to its second variable. So it is R is smooth. Let's say it can be it has as much derivatives as you want, but it has to be decreasing, and the derivative with respect to I is bounded and is never zero. Okay, and there are also assumptions on the smoothness of R, which are only technical. These are the hypotheses on the parameters of the problem, and there are also some hypotheses on the initial data. As I said, U has to be coercive. It can be recast as exponential minus U over epsilon bounded. The initial data has to be localized between the initial I, so the I computed with the initial data has to be localized between the two constants I introduced before, and the fact that U at initial time U is coercive can be well, it has to be a bit more quantitative to be able to do the computations. So we suppose that it is above something which looks like a triangle, and it is also under another triangle. And this hypothesis is not needed for the analysis of the continuous problem, in fact, but it is technical and needed for the numerical analysis. We suppose that the initial data is Lipschitz. We denote its Lipschitz constant L0, and well, it's a technical assumption. L0 is large enough such that it is greater than this A bar. And as I said, U is supposed to be, when epsilon goes to 0, we expect that the minimum of U is 0, so we suppose that this is also true for the initial data. Well, and under these assumptions, there is this result coming from this paper in 2009. Suppose that the initial data converge to something which is smooth and so on when epsilon goes to 0. The proof is only done with a compactness argument. So you have to extract a subsequence, and you saw that you know that this extraction converges locally uniformly to a function which is continuous. So it is more regular than only a measure, but it's not really it's not as regular as the solution as a reaction diffusion equation, for instance. And in fact, the good regularity assumption is Lipschitz, so you can't expect more regularity than continuous. And this V is the viscosity solution of this equation, which is actually a Hamilton-Jacobi equation, dTV plus the square of the gradient of V, n equal to minus R of xj, and j is a constraint. Actually, it is a Lagrange multiplier which is determined such that the minimum of V for all time is 0. So this theorem actually gives the existence of a solution of this equation, this constrained Hamilton-Jacobi equation. But in this paper, the uniqueness was lacking. Okay, and it is in fact a complicated problem, since in J has only BV regularity, meaning that it can have jumps. And since it has jumps, the Hamiltonian in this Hamilton-Jacobi equation, if J were given, the Hamiltonian is not continuous in time, but if I'm not mistaken, the classical framework, or let's say the easy framework for Hamilton-Jacobi equations is when you suppose that the Hamiltonian has a Lipschitz dependence in time. So it is a complicated problem, and the uniqueness is a more recent result in this paper of Vincent Calvez and Matthew and Lam. And the uniqueness is composed of two theorems, meaning that if you consider the previous problem P naught with two solutions, so the solution V is Lipschitz, and the solution J is BV. There are two solutions with the same initial data, then they are equal. So for B, since they are continuous, they are equal everywhere. For J, they are only in BV, so they are equal almost everywhere. And this goes with another result, meaning that if you consider J as a source term in the equation, so in the Hamilton-Jacobi equation, so now it's not a constraint problem anymore. J is given, and you consider V as the viscosity solution of this Hamilton-Jacobi equation. Then there is a unique solution. Okay. And these two results enable, in fact, a strategy to treat the problem P naught. You can have some information on J, and consider J then as a source term in the equation. And if you are able to prove by other means that the minimum of V is 0, it gives you that V is the only solution of P naught. Okay, so these two theorems are very complementary. Okay, well, and this is only for the theoretical aspects of the problem, but in fact I am interested in the design of asymptotic-preserving schemes. In fact, schemes for this problem P epsilon, which is the original equation for U epsilon. We saw that when epsilon goes to 0, the solution of P epsilon converges to the solution of the problem P naught. And an asymptotic-preserving scheme is a scheme for the problem P epsilon. So it is convergent to the solution of the problem P epsilon when the discretization parameters, they are denoted H here, go to 0. And when the discretization parameters are fixed, and when you make epsilon goes to 0, you obtain another scheme, and you require this other scheme to be convergent to the limit problem, to the solution of the problem P naught. Okay. In fact, it is well, to say it differently, it means that you require the scheme to have a stability properties when epsilon goes to 0, so that the solution of the scheme does not explode when epsilon goes to 0. And moreover, and this is an additional property, you could be stable in the transition as epsilon goes to 0, but not a good scheme for the limit problem. So in addition, you require the limit to be a good scheme for the limit problem. Okay. Usually, and this is a very important difference with asymptotic-preserving schemes for kinetic equation. Usually, when you design an AP scheme for kinetic equation, the hard problem is the design of the scheme and the proof of its behavior when epsilon goes to 0. Usually, it is relatively easy to have this arrow, so the convergence of the scheme when epsilon is positive. And well, in most cases, I know there may be So some counter examples, but in most cases I know the limit problem is very simple, and so the limit scheme is very simple too, and it's not very complicated to have this error. For instance, if you are looking at the diffusion limit of a kinetic equation, the limit equation is a diffusion equation, and it is very easy to have a scheme for the diffusion equation. And if you have the scheme, it is very easy to check that it is a good scheme for the diffusion equation. Okay, in this case, this is the contrary. The scheme for epsilon fixed is very simple. The limit when epsilon goes to 0 is not really complicated. It's a bit technical, but it's not really complicated. And the hard part is to show that the limit scheme is a good scheme for the limit equation, because the limit equation is much more complicated than the original problem. This is the only reason, in fact. Okay, so let's go. The scheme, as I said, is really easy. You had there was a time derivative, so I approximate with a finite difference in time. In fact, all the scheme is designed with finite differences. Well, I skip H for the moment. You had epsilon times the Laplacian, so you use the usual approximation of the Laplacian. You had this net growth rate, so the term in R at place X and at time and evaluated at I of t. And it is important to consider this I implicitly. Okay, I was the integral with respect to the trait of psi times the exponential minus u over epsilon. So it is approximated with a quadrature rule. The thing that is important is the approximation of the Hamiltonian. The Hamiltonian, I remind you, it was the square of the gradient of the solution. Okay, so the square, it was gradient of u squared. And when epsilon is fixed, you can choose what you want. But since we are wanting the scheme to be stable when epsilon goes to 0 and to be convergent towards the limit scheme, towards the limit problem when epsilon is equal to 0, it is important to put a good approximation of the Hamiltonian in the scheme, even when epsilon is positive. Because when epsilon is equal to 0, we will recover this Hamiltonian. And for Hamilton-Jacobi equations, we usually ask the Hamiltonian to enjoy monotonicity properties, meaning that it is increasing in, well, not decreasing in its first variable and non-increasing in its second variable. It has to satisfy the fact that if it is evaluated in something negative and something positive, it is equal to 0. And it enjoys a consistency, meaning that the numerical Hamiltonian evaluated at the same point is the real Hamiltonian. It means that this numerical Hamiltonian here is equal to evaluated in P, and P is equal to P squared, okay, in this case. Well, so there is a choice, which is for this very easy Hamiltonian h of p equal to p squared. We can choose the Hamiltonian like that. But the things that are important, in fact, are these properties. Okay. And now we have to study this scheme. So S epsilon. When epsilon is positive, to check that it is a good scheme. When epsilon is going to 0, to check that it enjoys stability. And then when epsilon equal to 0, to check that this is a good scheme for the limit equation. So the outline is very basic. We start with a positive epsilon, we make it go to 0, and at the end we have epsilon equal to 0. Okay? Well, the convergence of the scheme when epsilon is positive is not really a complicated result, but I will give some details because it gives some tools for what comes next. The result is the following. You have stability condition, so CFL condition. It is for those who are not familiar with numerical analysis. It is a stability condition. It is a relation, between the time step and let's say a space step or X step, to make sure that the scheme is stable. And stability means that the numerical solutions does not explode. Okay, and there is this kappa depending on R. So there are many constants arising, but well, it's technical, and under these conditions, you have the following result, meaning that the scheme is convergent if you evaluate the solution U epsilon at time tn plus 1 and xi, and you compare it with the solution of the scheme at n plus 1 and I. So it is small, meaning that the error is a constant which depends on epsilon times dt times the logarithm of dt and plus dx. Okay, and there is the same result for I. Well, just a remark, this proposition is only for fixed positive epsilon, and when epsilon goes to 0, this constant increases. It explodes. It can explode. It depends, in fact, of the properties of R. But if no further assumptions are done, it can explode. Okay, so it is a result for epsilon positives, but if you fix, for instance, epsilon equal to 1, it means that the scheme F epsilon is a good scheme for the problem. Well, to prove it, the idea is to reformulate the scheme by taking apart this quantity. I give its expression here, and it is in fact the monotonic part of the scheme. And if you take this monotonic part of the scheme apart, it's because the monotonic schemes have very nice properties. Thanks to the monotonicity, they preserve inequalities. It means that if you start with a solution U and a solution V, which respect an inequality, and you apply the scheme M, the image by M of these two sets of solution U and V respects the same inequality. Okay. Also, these monotonic schemes preserve discrete Lipschitz bounds. So meaning that if U enjoys discrete Lipschitz bound, meaning that UNi minus UNi minus 1 over dx is uniformly bounded, its image by M respects the same bound. And well, we are dealing with solutions which are not bounded in X, but if you consider two solutions which difference is bounded, then their image by M is also bounded, and it has this inequality also. Okay. Well, this monotonicity arguments is stability estimates, and once you have stability and consistence, it's not immediate that the scheme is convergent. It's only for linear schemes, but you can adapt the proof, in fact, of the convergence of the implicit earlier schemes for ODEs, and prove that the scheme converge. Okay, but the important argument here is the monotonicity of the scheme. Well, if you want to implement it, if I come back to the expression of the scheme right here, you see that it is in fact an implicit scheme. But if you plug the expression of U in the expression of I at time n plus 1, you have a closed equation on I that you can solve with Newton's method. Okay, you have to be very careful when you implement this Newton's method because of the 1 over epsilon. So it can you have to be careful, but it works. Okay, it is if you implement it carefully, it is the stability of the numerical computations for small epsilon, and in fact it also works on a truncated trig grid, because here I suppose that the grid was on R, the whole R, but not truncated. In practice, it's not possible at all. You don't have enough memory to put so many points in your computer, so you have to truncate. Since U is coercive, these quantities are expected to be very small after when it is far enough. So you can truncate and sorry, you can truncate and control the error when you truncate, and so you can prove that the truncated scheme converges also. Okay. Well, this is very usual. The important argument is the monotonicity, and in fact, the monotonicity. Okay, I'll skip this one. In fact, the monotonicity also gives the asymptotic behavior of the scheme when epsilon goes to 0. Because you have to suppose that another condition is satisfied. All the conditions I will give are compatible. It is just that it is more clear to separate them, but they are all compatible, and you can find dt and dx such that they are all satisfied. Okay. This stability condition depends on epsilon, and here we fix dt and dx, and we suppose and we show that when epsilon goes to 0, the sequence defined by the scheme S epsilon goes to another sequence V, and the sequence I defined by S epsilon goes to another sequence J, where V and J satisfy this scheme S naught, which is the limit scheme. And there is formally for V just the epsilon times the Laplacian disappeared, and the equation for I became a constraint on the minimum of V, and this is the equivalent of the stationary phase for stationary phase theorem for the integral I. Okay. Well, and the proof of this theorem also strongly uses the monotonicity of the scheme. So the monotonicity of the scheme gives you that the Lipschitz bounds of the initial data are preserved. They are a bit increased because of the net growth rate R. The bound from below, so the fact that U is over a triangle is conserved thanks to the monotonicity of the scheme. Well, because of R, the bond changed a bit, but the important thing is that it is over a triangle. You have bounds for I that are uniform with respect for epsilon, and you have the following estimate for the minimum. And it gives you, then when epsilon goes to 0, if you converge the fact that the minimum of the limit is equal to 0. Okay, and so once you have this stability estimate, you have the asymptotic behavior of the scheme. Okay, and on a numerical test, you can plot the U with respect to X at fixed final time, and for the different epsilon, we observe that it seems to converge to something. And exactly the same thing for I. So this is for the larger epsilon of the range. And when epsilon decreases, this yellow one, and after that you know this orange one. And the limit one is this one with the steps, because I remind you that I, when epsilon is equal to 0, and there is only a behavior regularity. And you see that when epsilon is positive, I is smooth, but it goes to it converges to something that is only BV. One other important remark is that the convergence seems to be very faster for U than for I, and this is related to the lack of regularity of I. Okay, one epsilon is equal to 0. Well, and the theorem of the asymptotic behavior of the continuous problem does not give any convergence rate in epsilon, but it is possible to do to have a conjecture with a numerical test. So if we plot the uniform norm of U minus U depending on epsilon minus the unit with respect to epsilon, we observe some decrease of order 1 in epsilon. And if we plot it for J in L1 norm, it seems that the speed of the convergence rate is also 1. So the error in L1 norm between I depending on epsilon and J for the unit scheme in L1 norm is of order epsilon. But in L infinity norm, well, if you're not familiar with numerical schemes, it seems at first sight that the decreasing is the decreasing is of order 1. But if you remark, there is a plateau here, and if in fact this plateau stops when epsilon is more or less of the size of the smaller discretization step. And it means, well, since the discretization is fixed in the numerical computation, we are in fact working in finite dimension. So it is expected that these two norms are basically have the same behavior because they are equivalent in finite dimension. Okay, but this is not a real behavior. Okay, this is only because the discretization is fixed. If we were changing the discretization and looking, so maybe refining the discretization and looking at the same test with another discretization, so a finer mesh, we would have got another plateau wider, and only after the epsilon, which is of the size of the smaller mesh, the discrepancy. Okay, so in fact, the good norm to study the problem for I is L1, at least numerically. Okay, and if you consider the continuous problem, you expect L1 too because it is only a BV function. Okay, so you can't expect a convergence in an infinity. Okay, so very quickly, when epsilon goes to 0, I won't give so much details, but if you are familiar with the finite volume schemes and with the compactness arguments for convergence, you know that well, the idea is that you define a function defined over 0 theta cross R, okay, which coincides with the scheme at the grid points. And why are we extending the definition of the scheme into a function? It is because we want to have the scheme, the stability estimates for the scheme give some estimates for these functions, and after that, since it is they are function indexed by a parameter, the discretization parameter, which is going to 0. If you have estimates in a good functional spaces, you can use compactness arguments and make the solution converge when epsilon goes to 0. So this is the idea of compactness arguments for the solutions of finite volume schemes. You have this theorem means that if you have the same kind of stability estimates, and if you make dt and dx go to 0 with a fixed ratio, and then the solution of the scheme converges to the solution of the limit problem when dt and dx goes to 0, and so and the same result for j. Okay. There are two items in the stability estimates, but no matter. Since it comes for compactness argument, we can't have a convergence rates. Okay, and so very quickly the ideas. The compactness argument comes from stability estimates, and it is only consequences of the monotonicity of the schemes and on the monotonicity of R with respect to its second argument. So you have uniform Lipschitz bonds for VDT in T and X. You have uniform bounds for JDT. Uniform with respect to dt. In fact, you have the fact that j dt is non-decreasing. Then you can make dt goes to 0, and it converges up to a subsequence to some v naught and j naught when dt goes to 0. And what remains to do is to identify this v naught and this j naught to the solution of the constraint Hamilton-Jacobi problem. But the big difficulty here is that j naught is only in a VV function. Okay, so to solve the problem, the trick is to regularize j naught and j dt. So you regularize it so that these j dt k are k Lipschitz functions, and the uniform bonds and the properties of j dt are preserved. So uniform bonds, non-decreasing. The regularization is monotonic also. And j dt is Lipschitz, k Lipschitz, and when k is fixed, you have uniform convergence of j dt k to j naught k when dt goes to 0. Okay, and once you have regularized j naught, you consider it as source terms in the continuous problem and in the scheme. Thanks to the monotonicity of the approximation, you have that the solution of the continuous problem regularized converge, but increasingly, let's say, to the solution to some v infinity limit, which is the viscosity solution of this Hamilton-Jacobi equation with j naught as a source term. And thanks also to the solution, to the monotonicity of R and of the approximation, the following inequality holds. And at the end, you use a viscosity procedure. You have to double variable and use an auxiliary function. You obtain that this v infinity is smaller than the v naught. Okay. You have to do exactly the same thing to have a reverse inequality. So v naught smaller than w infinity, and w infinity is defined basically the same way, but you have to define j naught a bit differently. But at the end, j naught and this other mathfrak j naught are equal almost everywhere, so that in fact w infinity and v infinity are equal because they are continuous. And by other means, you show that v naught has minimum 0, and it yields that you can identify the limit of the scheme to the solution of the constraint Hamilton-Jacobi equation. Okay. And so just a few numerical tests. You can plot the solution of the limit scheme with respect to time. It's just to emphasize on the fact that the scheme is stable when the solution has a only Lipschitz regularity. You can also plot J dt, so the constraint with respect of time, and observe that, so the constraint is in blue here. You can observe that it has a jump, and the jump arises at exactly the same time as the jump in the argmin of the, here at the beginning the argmin is on the left, and after some point, so between the yellow one and the green one, the minimum jumps from the left to the right, and this is the jump you see here. Okay. Well, it is possible to have an analytical solution if you consider a good initial data. You can compute an analytical solution of the limit problem, so we can check that numerically we have the same solution, and it works. And it also gives the tools to do an error study of the limit scheme, since we had only a convergence result but with no convergence rate. Numerically, on this analytic solution, we observe that the convergence rate is 1, both to V in an infinity norm and for J in L1 norm. Okay, but it's not true in an infinity norm for J. And we can also show that the scheme is uniformly accurate. Uniformly accurate means that the accuracy of the scheme does not depend on epsilon. So you plot the solution of the scheme S epsilon. So the error for given dx and given epsilon, you compute the solution of the scheme S epsilon. You compare it to, let's say, an exact solution for the same epsilon, and you obtain an error for given dx depending on epsilon, and you do it for many dx. Okay, and you observe stratified curves, meaning that the supremum in epsilon of this error is only a function of dx, and it goes to 0 when dx goes to 0. And the same property holds for I in L1 norm. But for I, if you consider other norms, so for instance, an infinity norm or the semi norm of the total variation, it's not true. Okay, so the uniform accuracy seems to be true only in L1 and not in an infinity or in the BV norm. Okay. Well, and to finish, just it also works. I presented it only in dimension 1 because it's simpler, but in fact it works in any dimension. So for the trait, and you can observe the initial data as a minimum here. After some point, it jumps, and this is for epsilon decreasing, and you observe the concentration very clearly, and this is the limit scheme. Well, for J, it works exactly the same way. But in fact, in dimension greater than 1, the results are not different at all in comparison to the dimension 1. Well, I will stop. I'm sorry, I was a bit long. To summarize, I presented an asymptotic-preserving scheme for concentration phenomenon in parabolic Lotka-Volterra equations. I proved its properties. The perspectives of this work are dealing with a more general mutation kernels and integral differential equations, so with integral mutation kernels. This is a work in progress with Benoît Godel, which is a postdoc in our team, and it raises also the question of the scheme for general constraint Hamilton-Jacobi equation, which is also a work in progress. And this is a very simple problem for a model arising in quantitative genetics, but it also raises the question of designing schemes for other models with other structures, and in particular structures in age, for which you have a boundary condition at the age 0, which is the image of the birth, and the structure is very interesting. Well, and I will stop here, and just a bit of advertisement for the CEMOAX, which is a summer school happening in July in Marseille, in the Siam, and after that there is a research session for students, so PhDs and postdoc of 5 weeks. If you want more information, do not hesitate to contact me. The team this year is transport in a very large meaning, so kinetic equations are very welcome in the CEMOAX. And thank you for your attention.
Thanks a lot. Thank you very much. Do we have any questions? Anybody has any question? No. Please.
I wonder if you have any idea on how to go higher order with this approach.
Well, it's not easy to answer because for the mid scheme we don't have any clue of the order of the scheme I just presented. In fact, if you want to expect high order finite differences schemes, in most cases, you need regularity of the solution of the continuous problem. Well, and in this case, we don't have such properties. Well, so to avoid the problem of the regularity, we should maybe use schemes coming from, well, with similarities as a finite volume schemes. But it's not clear, well, even for finite volume schemes, when you don't have a regular solution, usually you can't prove high order. You can have numerical tests showing that you have higher order schemes, but prove higher order is usually complicated. I don't know if I answered the question. In time, maybe it could work with a Lotka-Volterra scheme for time, maybe, but in trait, I don't know.
Any other question? I guess we are anyway late for our cake and coffee break. Thanks again, Helene.
Thank you very much.
So we will resume in actually 24 minutes, and we have a cake and coffee in the main part. And
thank you. Goodbye.